Our dear Heavenly Father, we're grateful for this day and for the chance we have to come to school and learn about transport. We ask you to bless our minds that we can understand what is being taught, and also bless Dr. Tree that he can present it in an understandable way. Please bless us to be able to be safe during this day and to get many of our to-do lists items done. And we say these things in the name of Jesus Christ.
Amen. Amen. I hope it's understandable. I hope it's even a little better than just blurry. Okay. Hope we enjoyed a little bit. All right, so it's our last. We'll just spend just a few minutes today finishing up what we didn't quite get to the end of on vectors answers last time. Remember, we were talking about coordinate systems, and I gave you a little bit of math sort of flavor to coordinate systems and a little broader view, and then we investigated algebra and curvilinear coordinates, which we talked about what a curvilinear coordinate was, right? Distinguish that from other kinds of coordinate systems. And we talked about the algebra in them, which is the same, right? Thank goodness it's an orthonormal system, so that makes our algebra easy, okay? But then we have vector calculus, which is a little more messy, okay? And so we're trying to understand where these formulas in our book come from, all right? And our homework is to derive some of these expressions. So we're doing a little practice with derivations on the board, and so we're talking about where these things come from. So to do vector calculus in curvilinear coordinates, we need the del operator, right? The derivative operator, the gradient operator. And that gradient operator is defined in the standard basis for R3, which is Cartesian coordinates. So it's delta x, delta y, and delta z. Okay? And we want to convert that into something in, say, a cylindrical or spherical coordinates. So to do that, we have to convert. There's two different kinds of things that appear here, right? There's the unit vector and then the derivative, and we need to convert both of them. And to do that, for the unit vectors, we talked about how to get unit vectors. That comes from our relationships between r, theta, and z, for example. So I did cylindrical coordinates on the board just so you could see it all out. I had a few minutes to write it out while you were coming in. Okay. And so, but again, this, like for instance, is in the table. There's nothing, unique about this. I copied it out of the book 2 minutes before we walked in. Okay. So this is how I go between, the unit vectors and x, y, and z, and r, theta, and phi, right? And this is just matrix multiplication, so it's this times that, plus that, plus that, and that gives me delta r. So it's just a convenient way to write 3 equations out, okay? And then to get the derivatives, I need to do the chain rule, okay? And the chain rule gives me another matrix, okay? And, oh, I forgot to write the other pieces here. This one has d, dr, d, theta, d. Okay. So this guy is like this is a re-expression of this down here where I evaluated these dr dy's, d theta dy's, etc. And we did an example of that last time, if you remember. We just did this one, I think, dr dx, and we got cosine. We're going through that little process, okay? And what you need to do here then is invert this matrix to be able to get this guy back here, right? Because you need to substitute. Oh no, you actually don't. I lied. You just have dx. You substitute in r and theta, and then multiply them out. Okay. So that just becomes then algebra at that point. It might be a little bit painful, but it's not too bad. You just start multiplying everything out and rearranging, gathering together. And when you do that, you end up with this. Okay. Now, but maybe disappointingly, the only thing that changes is you end up with a 1 over r in front of the du thing. So maybe that's nice. Maybe you can see where that might come from, right? I have a 1 over r here. Everything else sines and cosines, and they all add up to like sine squared and cosine squared together, and I get 1s. And lots of stuff cancels out. Okay? So you can go through a similar process, and you end up with this for spherical coordinates. Okay? So spherical coordinates, you got to go back, do the same thing, but now with r, theta, and phi. And if I remember right, in your homework, you got to deal with spherical coordinates. Okay, that's all the questions are asking. All right, so the question is, okay, so if we have these expressions, great, we can do those operations, right? Like if we want to do, grad some scalar, or just some scalar, all you do is take these and put the scalar in, s, take the derivatives of it, right? If that's some scalar function, and off you go, okay? If you have a tensor and you do something like a dyadic product, it's the same thing, all right? You just put in the vector, here, s is probably the wrong thing to use because we usually use that for scalar, but now you have to do the derivatives of each component, right? And that's a little bit harder, okay? So when you go to do that, if I said grad v, that's another one. What do you do about taking the derivative of this v that now has unit vectors in it? So anytime I'm doing an operation on a vector, or if I end up, say, doing del dot, tau, or tau is a tensor, there's going to be unit vectors inside that derivative, and I have to be careful. Okay, I'm going to erase this. So that's what we're going to show for just the last little bit of this lecture. So we'll just do an example. Wonderful coordinate. Okay, so suppose I want to do del dot v. Well, I write out the definition. So I do delta r v r plus delta theta 1 over r d theta plus delta v d dz dotted with, and now I'm going to have vr delta r plus v theta delta theta plus dz delta z. That makes sense? Okay, so now I got to just multiply the whole thing out. So to do that, I'm going to take this one, multiply by that one, and that one, right? And then this one, multiply by that one, and that one, and so on and so forth. Okay, so looks like maybe okay, so let's just do that real quick. So I have delta r dr of dr delta r. I have a dot product that I can't forget, right? So the dot product right there. Plus I'm going to have a delta r dr v theta delta theta plus delta r dot dr dz delta, delta z. Okay, and I'm going to just cut that out there, just to sort of show a flavor of what's going to happen, right? So this is just from the first term. All I did was that one with those three guys. Okay? So I didn't do the other ones yet. There's more to go. So how do we evaluate a term like this? All right. So we need to know, is delta r a function of r or not? Okay. If it's a function of r, then I have to take that derivative carefully. I have to use the product rule and take two terms out. But if it's not a function of r, then I can just pull it out. I can always just do the product rule, but it gets really messy, right? Because I already have 3 terms and I'm going to have 9. And if I have to do the product rule on everybody, I'm going to have 18 terms. And that's really easy to make an algebra mistake if you do that. So you come over to your book and you come back and you can look at these derivatives of the unit vectors, right? We wrote down expressions for the unit vectors. So we know dr in terms of, that's right there. It's cosine theta dx, sine theta dy, or delta y, right? So, okay, so it's not a function of r, but you can look up, and BSL also does the derivatives of unit vectors for you, right? But we know this one, it's not a function of r, so we have delta r, you can pull it out, so we got delta r, and we have dvr dr, okay? This one, we have to look at delta theta. Is delta theta a function of R? It's not a function of R. So we can pull that one out. We get delta R dot delta theta d theta dr. And then the same thing for z. Z is only a function of z. So we're going to get delta R dot delta z dz dr. Okay. Now, that one was super easy because everything just popped out, right? But when I go through and do the next ones, I'm going to get that delta R, is a function of theta. So if I had to pick the theta I want to do, I would have to do the product. Okay. So in this case, now I have these two dot products. Well, I said this was an orthonormal basis. So this is 1 here, and that one's 0, and that one's 0. Okay. I end up with dvr dr. That's the only thing that survives from that. Okay. So I don't want to take the time to do all the algebra all the way out. Okay. But I'll do another one if it's still confusing. If you want me to see, to say to do one more term. But I'll write the final answer here. You can tell me if you want me to do one more. So the final answer, after a lot of algebra, playing everything out, is dvr dr plus 1 over r dv theta theta plus you end up with a vr over r plus dvz dz. Okay, so you have not only this 1 over r here, but you have this entire extra vr over r that comes out. That's maybe what you might not think if you just naively wrote down the del operator. Okay. Yeah, please.
So, Zach said in previous classes for the dot product, we always just multiplied the ijk terms with ijk terms and added them. Why do we do a formal following here?
You multiply by the ijk terms.
Does that make sense? So I'm just asking, like in the past with the dot product, normally we have like, I don't know, an ijk or an xyz term. And then when we dot it with another vector that's xyz, we usually just take the x term times the x term plus the y term times the y term. And so here I just thought it was interesting that we did more steps.
You're right. You're right. I'm wrong. You're right. Those don't exist.
But that is the way the book does do it. When they go through their example, they do multiply every single one and they end up with 9 different terms.
Okay. Well, okay, so this is just because this is, I confused myself. So it was actually okay to write that, but we'll just, so what goes on here is that normally, this is a good question. Let me write something else up here just to show. So if I write just v dot w, okay, you're saying normally we write this as somewhere over I of vi wi, right?
Yeah, exactly.
Okay, so if I wanted to, I could write this as v del r, vr del r, plus v theta del theta, plus vz del z, right? Dotted with wr del r plus w theta del theta plus wz del z. Okay, and the property that delta, I j or delta I dot delta j is equal to 0 and 1, right? If I doesn't equal j and if I equals j. If I take that and apply that, that's what gives me this. Does that make sense? Like, so multiplying it all out, and then the fact that I get delta r times delta r, that gives me vr wr. And then I have vr and w theta, that one's 0 because those are orthogonal. So that's this property of the dot product of the unit vectors is what gives me this formula. Does that make sense, Adam?
Yeah, that makes sense. Thank you.
So we sort of like jumped here, just sort of assuming, right, that we can do that dot product really quick. But when we go to take the derivatives, we have to be more careful than that. Does that make sense?
Yeah, and is that because the derivatives can actually give us the del operator for, or the delta of other directions?
It's because the derivatives depend on space, right? Remember that like cosine theta is changing as I go around theta. Like it's not pointing in the same direction. So when I go to take the derivative, right, it's different. So, you know, I have a d d theta of a delta theta, and when I go to do that, that's going to matter, right? And so I have to be careful about taking that derivative.
Okay, great. Thank you so much.
Yeah, so sorry. So these terms didn't need to be, I was just temporarily confused. So sorry about that. All right, so so my advice on this is to, you know everything you need to reproduce the entire appendix in BSL, okay? There's nothing you don't know. But if you go to do this homework, like you should do as much as you need to make sure you're comfortable. But then once you're comfortable, start pulling formulas out of the book, right? So like you should do it maybe the first time or the first 2 times, sort of all out to make sure you've done it careful, to make sure you can you know where everything comes from. Then after that, start using stuff from the book, and don't, like every time, don't reproduce, these kinds of matrices, right, all by yourself, and then normalize them again and do all that stuff, because you'll hurt your hand, and you only have so much money for paper and pencil, right? So you got to be careful about that. Okay, so I'll give one more just quick. One more quick comment just on integrals, because they'll come up periodically. And this is just, I'll erase this real quick. Just a quick comment on integrals. Okay. So to do an integral, you need, when you go to do, like a triple integral or a volume of something, right? In cylindrical coordinates, you end up with something like r dr d theta dz, right? And there's this r here, okay? And the question is, so where does that r come from? Why do we need it? And that r is, you might have learned it in calculus, like the differential volume. So you look at the differential volume of some chunk, okay? Another way to get it is by taking the determinant of the Jacobian matrix, okay? Or the Jacobian matrix, I'm gonna write something really general and then we'll talk about what it is dfi d little fj, okay, where this means determinant, okay? And this is the matrix of unnormalized partial derivatives from the basis vectors. Okay, so this is this guy right here, okay, except this one's already been normalized. So so when I say this EF, this F, if you recall, this was the F where I said we had something dx plus something delta y plus something delta z. Okay, and then now I'm taking the derivatives with respect to these fj's. That's like, for example, r theta phi, okay, or r theta c. Okay, so that's where I go through and write out. This was my function, right? That had the space curves that described my coordinate system. Okay, and then these are the various variables that I use to take the derivatives with respect to those. Okay, and if I take all those derivatives and make a matrix of them, and I take the determinant, that gives me this R. Okay, that's another way to think about getting it. So I just sort of wanted to make that comment so you could maybe make a sort of have a full connection to this idea that we have of these space curves defined up there. And another way to get this is by taking determinant of J is also equal to delta 1 dotted with delta 2 cross delta 3. Okay, where that one might be R Z or R. Okay, so it turns out that the determinant of that matrix is given by that same product. Okay, so you can, that's an easier way probably to think about doing that. Okay, all right, so that's where that comes from. All right, so I think that's everything I have to say about vectors. Questions about that or about how to do your homework on that? All right, talk about the Brigham family stuff. Yes.
So on the dot product question that we were just talking about,
Yes.
so basically for these derivatives, sometimes that rule where if I equals j, or if I doesn't equal j, then it equals 0. Sometimes that's not the case because the unit vector depends on.
Okay, good question. Okay, so that dot product rule, this idea that delta I dot delta j is equal to 0, 1. This one's I not equal to j. This is I equal to j. Okay, that's always true. What happens is I have this derivative d theta of v theta delta theta. Okay, and this guy depends on theta. So what's going to happen is I'm going to get delta theta d theta d theta plus v theta d delta theta d theta. Okay, and then that guy might give me something that has other terms in it, right? So I have to be careful about that. And so that might end up being, like cosine theta dr plus sine theta delta theta or something like that, right? And now once now that comes from that derivative. Once I do that out, now I take this, delta theta out front of the dot product, right? And now I have to have these delta thetas be outside a derivative in order to evaluate that dot product, right? I'm not allowed to just move things outside of a derivative unless it doesn't depend on that thing I'm taking the partial. Does that make sense? So this is always true, okay, for this orthonormal coordinate system. So we're okay doing this. What we're not okay doing is pulling terms out of derivatives if they're functions of that thing.
So if you once you do get it to a form where you've taken the derivative like this over here.
That's right. Now I can just do delta dot delta r.
Yeah.
Right. And that's so that term will go away, right? But that one will stay. Okay. And when this one stays, now that's where I would end up, say, with the sine theta. I mean, I don't actually remember what that derivative is, so don't take that seriously. But does that make sense? That's a great question. All right, so this one I just decided we're just going to lump it together. I'm going to call this a lecture 11 and 12, right? And this one is on the momentum equation. All right. So we're going to start out. So So we're going to start out with deriving transport equation. A, we're going to do the momentum equation. And B, we're going to do the continuity equation. C, we're going to take a little aside and talk about Lagrangian versus Eulerian derivatives. I'll call that for derivatives. We'll call that frames. Okay. And then is there a D? No. And then we're going to do two. Do simplifying and solving Navier-Stokes. And we'll probably have some more A, B, and C, but I'm sure we won't get there today. All right. So we've kind of been waiting for this a long time. I'm excited that we're finally here. So we started out, we learned about viscosity and the constitutive law, right? And we did that for heat transfer, we did that for mass. Then we went back and we talked about shell balances, okay? We did these 1D momentum balances where we had to use that constitutive law and plug it in. Okay? And then we did the same thing for heat transfer. We haven't done it for mass transfer yet, for whatever reason, in the organization of the lecture. That's coming in a couple of days. But so we're circling back around now. We did all this prep with vectors so that we'll feel really comfortable doing the manipulation. And now we're launching into the full three-dimensional time or unsteady momentum equation. Okay, so we're going to talk about that today. We're going to get that equation and we'll see how far we get. So let's start out one on, call this transport equation. Okay, so A is the momentum equation. All right, so remember that I said that to derive a transport equation, we needed two parts. We needed a balance of some conserved property, and then we needed our constitutive law. So let's start out and do a balance. So we're going to do a 3D shell balance. Okay, and we're going to do it on a cube. So, let's see. Okay, remember, we did shell balances and we did them in never in three full dimensions. I think in our cylinder problem, we had 2 dimensions, right? We had these cylinders. We looked at the momentum flow through the top and the bottom and in and out, okay? And we could do this in a different geometry, but it turns out that we're going to drive the equation. We're going to get it in vector, in vector form. And if we put it in cylindrical, a cylinder here, we could also get it in vector form. But then the vector form means the same thing. And we just spent like 3 days, right, talking about how to go back and forth between the different vector forms and different coordinate systems. So like, might as well do it in the easiest one, get the equation, and then just use our knowledge of vectors to move back to whatever coordinates we want, right? So we'll do the easy one. So we're going to call this X, this Y, and this Z. And what we want to do is just look at, for this little differential box, so I'm going to call this point X, Y, Z down here in the bottom left near us. And the top right far away from this, that's going to be X plus delta X, Y plus delta Y, and Z plus delta Z. Okay, so this is just some, in some big tank or whatever, or around an airplane, this is just some little differential cube, okay? And we know from shell balances what's going to happen, right? I'm going to take the limit as that little cube goes to 0. All right, so what I want to do is look at all the momentum flow in and outside of that box. So remember, we had this momentum, this combined momentum flux, okay? And so over here, this is going to be phi xx at x that's going to flow in, right? So that's the momentum flux, and then there's the area of this side that we care about, and that area is going to be delta y times delta z, right? So that's going to be, I'll just write it down here, phi xx at x multiplied by delta y delta z. So that's an example of a flow in on one side, okay? And then we'll have a flow out on another side, which will be phi xx at x plus delta x multiplied by delta y delta z. Okay? So we're going to have these flow terms in and out, and what we want to do is do a balance on that. And if you remember, our balance said was we had momentum. How did I say it? I like it here. Well, it's the change in momentum in the box is equal to momentum flow in minus momentum flow out plus momentum that's generated by body forces, things like gravity, right? So if I have a gravitational force that's pulling everywhere, that's sort of generating momentum in that volume all the time, right? It's causing acceleration to happen. So what I need to do this balance is I need to find expressions for each of these four terms, right? So I'm just going to label them. I'll call that one 1, 2, 3, 4, okay? And then we can write down those terms. So I think, because I do a lot of talking, that let's do this, okay? Let's have you guys work on 1. Andrew, you work on 2. Roya and Brian on 3. And we got the marks on 4, okay? So see if you can write down 1, 2, 3, 4, okay? And then turn around and I guess I'll talk to Andrew, but turn around and talk to each other in, I guess, a physically distanced way and see if you can come up with your thing, all right?
What do you want Zoom to do?
Oh yeah, you guys are on, I forgot about the internet. Pick your favorite. I guess we only have Andrew doing 2, so Zach, you could do 2. I don't know, who else we have on there? We have Dan and Zach is Zach Lawless, right? We haven't heard from them.
Yeah.
Okay, yeah, pick one to work on for a second. Sorry, I spaced about the online people. Way to call me out. Yeah.
So what's the difference?
Yeah.
Yes.
Can you determine the component? The direction is like if I'm doing.
Yeah, so direction component on that phi x, right? So it's phi j. Oops. So the direction,
Like if I'm coming from the bottom, like.
that's the direction of the surface. So this is the direction of the unit normal on the surface. The component is the momentum component. So in this case, this would be the x surface and the x component, right? But there's also going to be the x surface and a y component of the momentum, right? That's flowing in, but it's like the y component of the momentum that's flowing in that side. The tricky one on this. I had XX, but the XY, I didn't even think about that. Because it's weird, right? Because you have like a y, like, but what you imagine is like, imagine like an arrow pointed in the y direction, right? It can still get flow, you know, it can still flow in that way, right? That's what's kind of, yeah.
So you're assuming that the flow is generally in the right direction, but just viewing that flow from the other side is what you.
Oh, that's what, yeah. So you're thinking there's you know, there's some complicated velocity field, right? And there's y component here, right? But there's going to be a different, you know, magnitude of the y component on the other side. So what you're really trying to find out here is how does the y component change across that direction? And so you can sort of think of it as getting brought in on one side, something happens in the box, and it comes out differently on the other side. Something magic happened in here to change the y component of the velocity. So you got to take into account how the y component changes and how the x component changes. Does that help? Yeah. Thanks.
Are you doing this like when you asked us to do 1, 2, 3, 4? Are we doing it for the whole cube or just for that face?
The whole cube. Whole cube. So if you got the face, you've got one of, you know, the three, right? So, because you're going to get this, you know, like, oh, I guess you got to do, yeah, if you're doing flow out, over here, these are the outs.
Yeah.
So let's say that to make it standard, let's say we got up like this. So the in will be at the x, y, and z, and the out will be at the x plus delta x, y plus delta y, z plus delta. It's my favorite part in the ChEn when I can see the wheels turning. But then they kind of get grumpy, you know, because it's like, just want to be done. You've confused me. Anyway. Should we start with the easy ones? Should we start with 1 and 4? I think those are the easy ones. Okay. All right. Ones. Did you figure out number 1?
I just realized I was doing number 2 instead of number 1.
Yeah. Were you doing 1 or did you do a 2?
I was doing 1.
Okay. What'd you get for 1?
So I was thinking, well, we generally would assume it's a steady state with this volume as it gets smaller and smaller. It doesn't have the ability to accumulate momentum. I'm trying to think of a more general way to write that in case it was transient.
Yeah, so think about this, right? So it doesn't have to be steady. We did steady before. Okay, it doesn't have to be steady. So what you want to write is the time change of the momentum in the box. So you're going to want to write the time change, right, of the momentum. Well, momentum is like, you know, mass times velocity, right? So to do that, what's the mass of our box? How can we write the mass of our box in the variables we already have up here?
Density times volume.
Yeah, density times the volume. So I could write rho delta x delta y delta z. Okay, and then I'm going to switch to index coordinates and just write vi. Okay, because I think it'll be easier to do the rest of this in index coordinates. So does that make sense? So that one I think is pretty easy, right? We have the time derivative of mass times velocity. Yes.
Really quickly, I still don't really understand index notation. So
Yeah.
I'm used to thinking of VI being like one particular component of velocity. Is that what you mean here, or?
I mean all three of them, right? So this, when I write this in index notation, VI, what I mean is the sum over I, VI delta I.
Okay.
Right? It's a shorthand, basically. And so remember the two rules of index notation are if I have a free index, that means it's a vector. And if I have a repeated index, so if I have VI, WI, right, that means I've got sum over I, sum over J, VI, VJ, delta IJ, which gives me a sum over I, VI, I guess this one's supposed to be WI. Okay? And so in this case, I end up with a scalar, right, when I have a repeated index. And here, when I have a free index, I have a vector. Okay? All right, yeah. Okay, so can we do 4? What do we say, Marks?
Gravity.
Gravity, right? So how do I write the gravitational force?
Like rho Q del X to Y dz.
Perfect. Right. Okay. So again, like it's just mass times, the gravitational acceleration, right? And one thing that they do, okay, in the book is they write a vector for gravitation, which is like 0, 0, minus g. Okay. And so then they have that gravitational vector so that we have this as a vector equation. So we'll put a little I on the gravity, okay, to say that it's a gravitational vector. And that makes it general. Suppose we rotate our coordinate system or something, and we wanted to write gravity not as XYZ, then we can put it in whatever coordinates we wanted, right? So like in the falling down a film, I think you might switch your coordinate system potentially, and then you have gravity have cosines and sines in it. That would change a little bit, but basically the same thing. Okay. Okay. What about in or out? Let's see. In. Is that you? Can you give us a term?
Well, I think I have all of them, and they're basically repetitive, right?
Okay. Yeah. So give me one.
So so the one we did already, phi xx at x, delta y, delta z. And then you'd need the y dimension of that, so phi xy at evaluated x, delta y, delta z. And then phi xz, delta y, delta z. And then there's 6 more for every variation of phi and the two things, right?
Right. So I'm going to do this. Okay. So there's more like this. So we're going to go dot, dot, dot. So I'm going to write it in a slightly, I'm going to write these 3 like this. I'm going to write phi xi at x, delta y, delta z. You see how then I have my index goes over x, y, z. So that makes my life a little easier. And then I'm going to repeat that. So I'm going to have phi yi and then this one now has to be at y, right? Because now I'm starting, let's see, y is the one in front here. So that's going to have a delta x, delta z, plus phi zi delta x, delta y. Okay, so I'll put a little box here because it's kind of confusing. Okay, so there's really 9 terms there, right? Because of the repeated I index. Okay. All right, so now 3, what do you think, Roya?
All of these plus delta.
That's right. All of these, that's right. So I have a phi xi at x plus delta x, right? Delta y, delta z, plus phi yi at y plus delta y, delta x, delta z, plus phi zi at z plus delta z, delta x, delta y. Okay? Whew. All right, so let's see. Someone on Zoom, what am I gonna do next? Right, when we do shell balances, what happens next? I said Zoom, Andrew, come on, man.
So now you combine your terms and then you divide by usually the stuff on gravity, and then we just take the limit and put it in a derivative form.
Exactly, perfect, okay? Was that Zach that said that? Dan, perfect, Dan, okay. Right. So the thing remember is you divide by the volume, right? So he said that, he said the thing in gun of gravity. So you divide by delta x, delta y, delta z. Okay. You put them all together. So let's look at what's going to happen here. I don't really want to write this all out again. Okay. Like my hand hurts a little bit. Okay. But look, I'm going to have this guy plus this guy minus these guys plus that one. Right? And so I'm going to divide by delta x, delta y, delta z. So I'm going to get b dt of, and if I divide by delta y, delta z, I'm going to get, what is it? Rho, that's it, right?
Yeah.
Oh, vi. Like there has to be something else. We're not doing continuity. Okay, rho vi. Okay. And then I'm going to have this guy minus that guy, right? And when I divide by delta x, delta y, delta z, the only thing that stays is the delta x, right? So I'm going to have phi xi at x minus phi xi at x plus delta x divided by delta x. Okay, and I have the same thing here. Phi yi at y minus phi yi at y plus delta y divided by delta y plus phi zi minus or at x minus phi zi at x plus delta x. Okay, divided by, or excuse me, this is supposed to be a z. Not going too fast. Z plus delta z divided by delta z plus rho gi. Okay, now I take the limit of delta x goes to 0, delta y goes to 0, delta z goes to 0. All right, and notice that this is the negative definition of the derivative because I have the delta at the end. Okay, so when I get that, I get d dt of rho v. Oh, I'm doing index notation. Rho vi is equal to d dx of phi x I minus d dy phi yi minus d dz phi di plus rho gi. Okay, that here I have dx phi x, dy phi y, dz phi z. That's a divergence, right? So let's write that. We have d dt of rho vi, and in index notation, I write minus d dj of phi ji plus rho gi. I'll write that out and gives a notation because I think that'll look nicer for you guys. d dt of rho v is equal to minus the divergence of phi plus rho g. Okay, we'll stop there today because we're out of time. Okay, so we did a momentum balance. So what we're going to do next time is we're going to plug the terms in for phi that we already know. All right, we'll get a combined, or we'll get a what we call the Cauchy momentum equation when we do that. And then we're going to see we have the tau, which is the Newton's law of viscosity. We'll plug that in, okay, and we'll end up with the Navier-Stokes equation after a little bit of work. All right, so that's where we're going next time. Okay, so you have a couple homework problems on. I think I'm going to go back and look at the homework problems that were from. There was one from chapter 2 and one from chapter 3. I'll just make sure based on where we got today. I'll probably leave the one on chapter 2 on so that we don't stack up too many problems for next week. Because I think it was pretty short. I have to double check. I don't remember which one that was. So probably one of those problems will probably stay for sure. They're both really easy because one was like a plug and chunk and just to sort of do momentum balance stuff. So we'll go back and look at that and make sure that So you guys can do that. Okay, so thanks for the attention today. This is a cliffhanger. Old show called Alias. Did you ever see Alias? Remember that show? Yeah. This was on in the early 2000s. It was when I was like a junior in senior high school. So now it's on Amazon Prime. I'm watching it the other night. And it always ends on kind of like 24. Have you seen 24? Like 24 always ends on a cliffhanger, right? And then it's like resolved within the first 2 minutes of the next episode. You're like, why did I even care about that stupid cliffhanger? Like the gun's pointed right at him, and he's like, no, don't shoot. And then like you come back, you're like, how's he gonna get out of it? And then he just jumps out of the way, you know? And you're like, well, that was a stupid cliffhanger. We could just jump. Who knew that? I didn't know that was allowed.
So, Brad has a question.
Oh, yeah.
on why the traditional cross product doesn't work in circle, but then he just logged off. Okay.
Here.
Oh, are you here?
Are you still here?
Yeah, I'm still here.
Oh, that's weird. Like, I don't see him, but yeah, definitely.
I'm a
just-
ghost.
I think it does work, and this cross product does work like that in spherical coordinates.
Okay, because I was trying to work with ChEn on it because I tried that for one.